Welcome to lesson 36, Magnetic Fields and the Motor Effect. Today we start magnetism. Here's the plan for today. A magnetic field is drawn the same way as every other field we've met before. Lines of force running from north to south outside the magnet. And just as with gravitational and electric fields, the spacing tells you the strength. Lines bunched together mean a strong field, lines spread out mean a weak one. Same convention throughout. This time though, instead of mass or charge, it's magnetic objects that align themselves in the direction of the field. So the wire, with charge running through it, feels a force. But in which direction? This is where we need Fleming's left-hand rule. Hold out your left hand with the thumb and first two fingers all at right angles to each other. Thumb is the force or direction of motion, your first finger is the B field, and the second finger is the current, I. FBI. Thumb first, second. Make sure that they're all perpendicular. Now a question worth thinking about. What happens if you flip one of them? Say, reverse the current. Then the force reverses. And if you flip two of them, reverse the current and the field, they cancel, and the force ends up back where it started. That's vector magic, and it's worth playing around until it's automatic. How big is this force? Think about what it ought to depend on. A stronger field, B, should give more force. A bigger current, I, should give more force. And a longer wire, L, the bit sitting in the field, should also give more force. All three are directly proportional, so we simply multiply them together. F equals BIL, clean and simple. And that equation hands us the unit of B. Rearranging for B, you get force divided by current times length. We give that combination a name, the Tesla. So a magnetic flux density of 1 Tesla means 1 Newton of force per amp per meter of wire. Define it from the equation and you'll never have to memorize it. We should very briefly discuss how we actually draw these fields, rather than with lines and arrows. The way that we draw a field pointing towards us, outside of the page, is with a circle and a dot in the middle. If the field is pointing away from us into the page, we draw it with a circle with an X in it. Think about this as an arrow. If the arrow is pointing towards us, we see the front small tip. If it's pointing away from us, we see the feathers behind it. This is like the dot and the X. Now take that wire and bend it into a rectangular coil, sitting in the field and free to rotate. The current runs one way down one side and back the other way down the opposite side. So by the left-hand rule, the forces on those two sides point in opposite directions, one up, one down, and two equal opposite forces separated by a distance produces a turning effect, a moment, a torque. That's an electric motor. The torque is force times distance, with the force being BIL. When the coil rotates away from its ideal position, it presents a thinner slice to the field, and that introduces a cosine. Put it all together and you get torque equals BANI cos theta, where A is the area of the coil and N is the number of turns. I want to finish this lesson with one idea that ties this whole topic together, including the next few lessons. The whole of magnetism is about cutting field lines. The force on a wire depends on how much field it sits across. The torque on that coil depends on how thick a slice of field lines it's cutting through. And when we come to induction in a couple of lessons, generating a voltage will turn out to be about cutting field lines too. Hold on to that phrase, it will keep paying off. And that brings us to the end of the video. Thanks for watching and check out my tutoring page below.